such as simulation of the subaurora polarization streams, the plasmaspheric plume, and the SED plume. The MAGE model gives fairly good model data comparison so far, and we feel very encouraging to keep working on the model. The reason we want to study the geospace weather is we live with a star, and it connects to the Earth by the solar wind. The corona of the sun is the origin of the solar wind. It extremely hot temperature exceeding 1 million Kelvin. With such thermal energy, plasma stream consisting of electrons, protons, and alpha particles can overcome the gravity of the sun and escape from the upper atmosphere to the interplanetary space. Figure 2 gives a simplified description of the heliomagnetic equator, above which is above and below which is IMF directing outward or inward, and the perpendicular direction of the heliomagnetic equator does not necessarily happen to align with the rotation axis of the sun. So magnetic flux emitted from a fixed point of the rotating surface form a spiral trajectory, and the magnetic field line moving with the plasma will also twist like a spiral. And combine the two effects, we will see that the heliomagnetic field turns into a very wavy structure. So when the solar wind reached the Earth, the orientation of the interplanetary magnetic field could be either northward or southward. When it is southward IMF, it will trigger the day-side reconnection, and the geomagnetic field will be open and dragged into the magnetotail. The magnetic energy stored at the tail region will squeeze, and the field will squeeze the field line, and it will trigger another reconnection, and the field line will depolarize. And you can see the aurora is produced due to the particle precipitation. If it is under a steady southward IMF driving, a convection pattern will be formed in the magnetosphere, as well as in the ionospheric footprint. The geospace storm may happen if there's a coronal mass ejection on the sun. At times of CMEs, high-speed plasma bursts erupt from the sun, and dense coronal content, along with large amount of magnetic energy, is released to the interplanetary medium, causing shock waves. Large ram pressure will impact the Earth's magnetosphere, and which leads to the geospace storm. Here is a DSD index, which is a measurement of the strength of the storm. So it measures the geomagnetic deviation, and due to the plasma content being brought into the inner magnetosphere, there will, a ring current will build up, and during the storm main phase, and causing a negative BZ component, and it takes a couple of days to recover by different particle loss mechanisms. So during the storm, there are important multi-scale dynamic processes we need to capture. For example, the magnetic reconnection on the day side and at tail, the convection and the depolarization, the bursty bulk flows, and magnetosphere generated currents and their closure through the ionosphere. And also the ionosphere thermosphere patterns of convection, heating, and conductivity, which are controlled by the coupling of ions and neutrals invoked by the current closure. And there's also some feedback processes, like the ionosphere conductivity regulates the current and enables the electrodynamics feedback to the magnetosphere. also upflow and the escape of the ionospheric ions will enable mass feedback to the magnetosphere. To capture these important processes, we propose the MAGE model to self-consistently couple the models that handle the different region and different physics. Here is a diagram with all the related model listed. So our CGS team have developed a mini version of the MAGE model involving the coupling of global MHD model and the Gemera, and also the ionospheric potential solver remix, the rain current model RCM, and the ionosphere upper atmosphere circulation model TaiGCM. Next, I will talk about its major component and the coupling algorithm. The best way to model the large-scale plasma transportation in the magnetosphere is a MHD description of plasma. Since we are looking at a comparatively longer length scale than the Debye length or the particle gyro radius, and at time scale which is longer than electron and ion gyro frequency, we also have quasi-neutrality and Maxwellian distribution in the global magnetospheric plasma. So apart from like high energy particles in the radiation belt, we don't need to consider like relativity, and of course we don't need to go to the quantum realm. Under the MHD approximation, we can treat the plasma as fluid that follows the Maxwell's equations, and our MHD codes solve the time-dependent ideal MHD equations, and ionospheric potential solver here is tightly coupled to the MHD code. It solves the Poisson equations with a field line current calculated at the earthward boundary of the MHD code. And in turn, the solved electric potential will be the boundary condition that feed back to the MHD. And now we employ the next generation MHD code, Gemera, which is a brand new code that follows some major considerations of its predecessors, the LFM code. If I think you heard of that, it's a quite famous MHD code. It uses the TVD scheme and for the plasma transport with shock regions captured quite well. And also the MHD equation is solved on a non-orthogonal E-grid, where it can places higher resolution to the areas of interest, and it has high resolving power with a relatively small total number of grid cells. And for example, this is a IJ plane of the Gemera grid, which is using the lowest resolution, but you can still see we exert a very high resolution on the 50, like within the 50 Elsha. So it has a like a very large resolving, a very strong resolving power, but it doesn't need like a large amount of computing resources. It also has a routine to maintain the zero magnetic field divergence, and the ionospheric potential solver called MIX is integrated. Here, well, here you can see in the Gemera, which is like a reinvention of the LFM code. It has multiple numerical upgrades based on LFM. It has extremely high resolving power and robustness. You can see that the its resolution can be as small as like 300 kilometers, which means the structure at that scale can be well resolved, which allows it to capture small scale physics in the magnetosphere, such as the ballooning, interchanging stability in a substorm. It also have it is also significantly faster than LFM, since it's much better parallelized and has concurrent coupling. You can even and it also have like great cross-platform portability. You can even run on your laptop. So when it comes to the inner magnetosphere, the MHD approximation is not quite enough. The energetic particles are trapped in the closed field line and perform gyro motions and bounce motion and drift motions. And in the drift velocity, it is propelled by the E cross B drift, the grad B drift, and also the curvature drift. The drift dynamics is especially significant in the ring current buildup. This is a like a test particle simulation performed by CHIMP, and it's using the magnetic field from Gemera. It shows that how the energetic particles being transported and get trapped in the inner magnetosphere during storm main phase. And we need a more efficient way than like a test particle simulation to simulate and model the ring current buildup. And this is the time that the ring current model come into play. The Rice convection model is a widely used ring current model. The plasma population is represented by multiple like channels of electron and ion fluids with associated different energy environments. And it requires the magnetic field inputs and information of plasma moments when it's run. And all the fluid channels are considered at the equatorial plane, but you can map them to the ionosphere by the geomagnetic field lines. And also it is important to remember the RCM requires certain assumptions of quasi-static process, which means the process should be adiabatic and slow flow. Traditionally, RCM has its own MI coupling routine, and the electric, and also it has a electric potential solver. In the coupling to an MHD code, only part of the functionality has been used. So it mostly it uses its drifting advection. RCM calculates the kinetic energy of each flow channel to get the advection velocity and the particle population eta in each in unit flux tube based on some certain statistical distribution. And in our case, it's Maxwellian distribution. And also it solves the advection function of eta with the consideration of loss mechanism such as precipitation or charge exchange. Here is a diagram of two-way coupling of Gemera and RCM. At each exchange cycle, the information of plasma moments, including plasma density and plasma pressure, and also Gemera calculated a flux tube volume has been passed from Gemera to RCM. And also the electric field calculated by MIX has been passed indirectly to RCM to drive the E-cross speed drift. And in return, the RCM will redistribute the drifting plasma and feeds back the plasma density and pressure to the MHD. In terms of the coupling algorithms, we add some new options such as the plasma beta based limiting in the RCM feedback. In the high beta region, you can see the portion of RCM pressure has been scaled down, which means we think because of RCM's assumption of adiabatic processes, we don't want it to like dominant when beta is high. So that's why we scale down the portion of RCM plasma profile to ensure validity. And if at like plasma beta equals to 0, and the feedback pressure will be entirely the RCM pressure. Also, we had an F-wing bounce period used to control the ingestion timescale. So at lower F-wing speed, longer ingestion timescale for a better flux tube equilibration. The F-wing bounce period is basically the the flux tube length divided by the F-wing speed. We also experiment with a new RCM boundary condition. So previously, we only update RCM at its boundary, and whenever there's a new grid points enter into the RCM simulation domain, we fill it with MHD MHD data. But at the like padded region, for example, between the RCM boundary and also the open closed boundary, the old routine is to have a zero flow assumption, which means this area are all padded with the same value as the boundary. At this time, we tried a different upgrade algorithm. We set the padded ghost cell with all the MHD data. So it will be a more aggressive way to make use of the MHD input. So we compare the old round and new round. We find that will be more dynamic in the inner magnetosphere. To further couple to the thermosphere, we implement the connection of a combined electron precipitations from the magnetosphere to the upper atmosphere. One is a monoenergetic electron precipitation from MHD. The potential drop follows the equation of Knight's relation, and it exists at places the thermal flux is insufficient to carry the field line current. So the electrons are accelerated by the potential drop. And the other one is a diffuse electron precipitation informed by RCM, which is an integral of energy flux of loss cone electrons over all the energy channels. Basically, it's a thermal flux. So this is like a statistical distribution of both precipitations. You can see its spatial distribution and the strength. So I will mention it later in the model data comparison. The electron precipitation then is mapped to the TiGCM model, which is a thermosphere, ionosphere, electron dynamic general circulation model. It solved the 3D fluid dynamic equations for oxygen ions, it's O+, and other ionizable neutral constituents, such as nitrogen and oxygen molecules and oxygen atoms. It also calculated the production rate of the ionized species using the ionization rate. We can see that in the ionization rate, this is a flux this is the number flux of the electron precipitation, and also this is a characteristic energy of the Maxwellian distribution, which is a half of the average energy in the electron precipitation. So when we give TiGCM these two quantities, it will automatically feedback generate a ionization rate at that location. Once you have the ionization rate, the electron ion density can be tracked and used for the calculation of more self-consistent and realistic ionosphere conductivity. Here you can see if you get the ion distribution, you will get an average mass of the ions, and which decide the cyclone frequency that reflected in the Peterson and Holt conductivity, and also the ion neutron and electron neutron collision frequencies are decided by this neutral densities, which are like actively tracked by the TiGCM model. Here is two examples in the simulation that how the conductance is shown in the TiGCM output. So the conductance in the coupling will be feedback to the remix solver, which is a potential solver. So we will get a more self-consistent result in the electric potential. Another new development is a dynamic plasmasphere modeled in the RCM. So historically, RCM uses a 2D static density profile that comes from the Gallagher model. However, there is no change on the plasma pulse region during the storm time. And it often causes too much resistance to the plasma inflows, which may lead to strong instability and inaccurate ring current location. It also has this overcooling effect because we have too much cold mass in the magnetosphere. The overcooling effect will causes like underestimation of the average energy and the power of the electron precipitation, which lead to weak response from the ionospheric conductance due to insufficient heating and ionization. So we have implemented a zero energy channel in the RCM for the dynamic plasmasphere. It follows the drift kinetics and driven by the electric field and the corrotation. In each coupling cycle, RCM feeds back pressure that is a combined density to Gamera. So it will substantially and self-consistently feedback a cold population to Gamera without overcooling. And during a southward IMF driving, you can see the plasmasphere shrink its size This is its initial condition, and this is after a steady southward driving. You can see it shrinks in size, and also there's a realistic plume is produced. The figure at the bottom is a comparison of the electron precipitation power using the static Gallagher model as a plasmasphere, and also the dynamic one we are having right now. You can see the precipitation power is substantially increased, we like put into a simulation like of a certain event, and we calculate the ratio of the monoenergetic and diffuse precipitation, and it gives a really good agreement with a new observational data. So like 2/3 of the total power is contributed by the diffuse precipitation, and also you can see the spatial location of this precipitation also agree very well with statistical data. So we're very confident to say we're now heating the ionosphere with the right amount of energy. To this end, we have completed the diagram of a fully two-way coupled MIT system with all the components working self-consistently. And now it's time to do some application with it. So first is a subaurora polarization stream. SAPS are a westward stream or ion flow located between earthward boundaries of the downward region of downward region 2 current and electron precipitation. A strong E cross B drift is due to a strong poleward electric field at the conductance trough. Sorry, excuse me. Well, the region 2 FAC needs to be closed. Sorry, excuse me. The March 17, 2013 storm is a good example to study SAPS. However, previous simulation results are not quite satisfying. Here is a movie of variables in the RCM domain. So the top two panels show the plasma entropy and pressure. During the storm main phase, you can see multiple low entropy plasma inflow coming from the RCM boundary. The pressure gradually builds up, and the plasma pulse shrinks and it gives its way to the ring current. And the diffuse aurora is prominent whenever there's a strong plasma inflow. The mini-MAGE model, I think this one is using the Gamera plus RCM. It gives so far the best agreement with the observation. So 70% of the SAPS has been detected by DMSP are captured by the model right on spot. So if we check the source region, the downward region 2 current is mostly determined by the ring current pressure. And is pressure which is dominated by the ion distribution. conductance is mostly contributed by the electron precipitation, hence dominated by electron distribution. So this is a strong evidence of self-consistency that we're having accurate storm time pressure distribution. Field line and also field line mappings and ionospheric electrodynamics. So if you want to capture the observation fairly well, you basically have to have every component right to have this great agreement. Another topic that is closely related to the SAPS electrodynamics is magnetospheric plumes, which is my personal interest at the moment. The observation shows that the plasmasphere plume and SED plume, which is a storm-enhanced density in electron, have strong spatial correlation. So if you map both to the equatorial plane or to the ionosphere, you will see they actually overlap each other. Although we don't have a direct mass conjunction between the two regions right now, it is still interesting to see the evolution of storm time plumes in response to the ionospheric electric field. Here is a Gemera RCM Thai GCM ROM, which is a fully coupled mini-MAGE. Please see the white dot here. Where this two dots means they are mapped by the field line, and here we can see the SED plume is generated, as well as the plasmasphere plume. This is the equatorial plane view of the plasmasphere, and this is the ionospheric view of the same variable. This is MHD density. So when it comes to the model data comparison, we find that the simulation results give a very good agreement with the observation in the plasma pulse location, and the shape and direction of the plasmaspheric plume is quite similar with the observation around 21 UT, and also the spatial overlap of these two plume has been reproduced by the model. Also, another thing to mention is this is actually like a 400 nanotesla DST superstorm, and our model handled it pretty well. It doesn't crash or anything. It just complete the whole run smoothly. So to summarize, our newly upgraded MIT coupled model has shown significant improvement in self-consistent storm time dynamics modeling as a part of the Geospace system. In the near future, MAGE will span its domain to the whole geospace, from the lower atmosphere to the thermal sphere, ionosphere, and to the different regions of the magnetosphere. It will give better results in storm time dynamics modeling and also other critical mesoscale process across all the different domains. And And we think that high precision algorithms are the key component to capture the critical dynamics at a reasonable computational cost. So that's all the content I have today. So thank you, and questions.
All right, thank you very much. I guess we could raise hands or just unmute yourself and ask questions.
This is Slav American here. Shanshan, just a question about the overlap between the plasmaspheric plume and the storm enhanced density plume, the SED plume.
Right.
Why do you think they align so well?
Well, so if we talk about the real nature, that's like what's real happening in the nature. That is the ionosphere, the plasmasphere is actually an extension of the ionosphere. So basically, they have like tight mass connection between them. So if you refer to a RCM SAMI-3 simulation, you will also see a good agreement with those two plumes. Basically, they are closely connected. But in our simulation, although we don't have this direct mass connection, we have an individual plasma that evolved in the RCM, and also TiGCM that tracks the electron population. But we actually indirect feedback those connection. For example, we have this plasmasphere density feedback to the MHD, and it will produce the electron precipitation at 2 TiGCM at a certain region with certain strengths, and it will solve electric potential that drive both population, drive the cold plasma in RCM, and also drive the electron density, electron population on the ionosphere. That's why if you can see this potential contour around 9 o'clock, so you can see it basically follows the shape of the potential contour, and and also in the SED and in the TEC profile, you can see this plume has been dragged by this convection electric field. I think that's the main reason that why they overlap very well. So, but another thing I want to mention is that we do this is a 48 hours of real-time simulation, and we do get a very good agreement at a certain time that this plasmasphere has a very agrees very well with the observation profile, which is very encouraging, because it's a sign that we basically get everything not ridiculous, because we do get this similar result as what nature has. Yeah.
Thank you.
Any other questions? All right, if not, final thanks to Shanshan for a great presentation.
Well, thank you, everybody.
Yeah, thanks for attending.
Okay.
Thank you.